We're doing flux integrals, which is one kind of surface integral. And here's what the flux integral is. I won't go over that again. And here was our general method of evaluating this integral. But in the case where the surface is z is a function of x and y, you look at this formula, if you want to call it that, and it's going to take, several steps. We'll have to take the partial of u with respect, partial of r with respect to u, then with respect to v, cross that, and then take the dot product. There are many steps, but if we know that the surface can be expressed this way, z is just a function of x and y, we can do many of those steps ahead of time. So let's see. Our r vector becomes x, y, and then whatever the f function is. That's what c is. And then our u and v are just x and y, because everything can be parameterized in terms of x and y. So our partials become these guys here. And then we can take their cross product. You know how to do that, and you get this. And then the ds is magnitude of it, which is this. So now we have another formula for ds, the differential surface. And this might be what you find in some of your textbooks. That can be used when finding the surface area or integrating over a scalar function over a surface. And you might have a textbook where you'll see these, but not this. In fact, I taught with that kind of textbook. If you had other ones, maybe the surface could be expressed as x as a function of y and z, or y as a function of x and z. You could derive by a similar method, similar DS's. So you can come up with like 3 different other formulas, DS. And when it comes to the flux integral, we can take it yet another step. You know, your F has a PQR. That's just what we name the components. So here is what we're taking a dot product. So we can also take that dot product ahead of it. And you end up with this kind of whole new formula for when z is a function of x and y. So instead of using this formula, you can use this formula. That's what I call in my course the PQR formula. The convention for what positive will mean will be in positive z direction. And what you integrate, now this picture, this region down in the XY plane has meaning. The region of integration, this region of integration here will be in the XY plane, and it will be like the shadow underneath the surface. You had a light infinitely above or below the XY plane, that would be the shadow that the surface casts on the XY plane. That's your region of integration. Let's do an example. Supposed to evaluate flux of this vector field over this surface. And by the way, we'll have another method to do this particular problem because this surface completely encloses a volume. We'll save that for later. That's going to be the divergence theorem. But for now, let's do it using the methods we know about. Well, this top, well, first, let's see what it is. It's this paraboloid, I guess, on the bottom, where z equals x squared plus y squared. And the top is just a constant, z equals 1. So this, where those surfaces meet then, is going to be this unit circle up at z equals 1. So this paraboloid goes out to a radius of 1. The top is flat, so let's see if the direct method will work on that. Let's see, our f is y squared x squared 5z. N is just, we'll use the positive z direction, so it's 0, 0, 1. Then f dot n will be 5z, and z is just constant on that surface, it's 1. So f dot n is just 5, which is a constant. You can pull that out of the integral. You're left with the area of the surface, and that's just a circle of the unit circle. So the flux out of the top is 5 pi, and it is upward. I mean, the convention was upward, we got a positive number, so the flux out of the top is upward. Now let's do the bottom. Well, we have there's our p, y squared, our q is x squared, our r is 5z. We have to put them all in terms of only x and y. P and q already are. R is 5z, which is 5x squared plus y, because that's the surface. Yeah, on the bottom surface, this is the surface. F is a function, or excuse me, Z is a function of x and y. And then, so that's what's the partial of Z with respect to x? 2x. Partial of Z with respect to y is 2y. We have all the pieces. Here's the formula. Put them into the formula. We're integrating over xy, or differential areas in the xy plane. The region of integration is what? What is the shadow of this paraboloid in the xy plane? It's a unit circle. That's our region of integration. So we'll use polar coordinates for that. And it gets a little bit tedious. You know, x is r cosine theta, y is r sine theta. Make all those substitutions for x and y. dA is r dr d theta. Don't forget the extra r. What are we integrating over? The unit circle. So r goes from 0 to 1. Theta goes from 0 to 2 pi. Here is the setup. At this point, we have, it's just a normal double integral. We can break it up into sums, and then those sums can be broken up into products. The good part is this big ugly mess here just turns out to be 0. I'm not going to go through this normal integration in detail. So this whole part becomes 0, and we're just left with this second part. You can see it breaks up into a product as well. And this part is not that. And we get a positive number. What is the direction of that flux? Flux we just calculated. When we use the PQR method, the convention is in the positive z direction. So we got like an upward flux. The problem asks for the total outward flux out of the whole surface, the two surfaces. So we have to actually subtract this number from flux from the top number. We've got 5 pi minus 5 halves pi. So our answer is 5 halves pi. That's the sign convention and how you use the PQR method. We'll do another example in a next recording.